Iya, udah minum aja. Udah tak bilang.
Klik dulu Kak di ini. Jangan share.
Tombolnya nggak? Nggak ada backup.
Yang paling paham. Udah pulang.
Ladies and gentlemen, our session is starting to go. Ladies and gentlemen, the initial video shot the final presentation 2023. I'm Dominik Šafránek, the MC for this session. First, I would like to introduce you to the first speaker of this conversation, Dr. Dominik Šafránek. Dr. Šafránek will present us with a topic about enablement and its application in quantum computing. And allow me to share a brief background of Dr. Šafránek. Dr. Šafránek from Czech Republic, and he's PhD from University of Rotterdam and the University of Australia, where he develops a new formula for the optimal estimation or concept of observational income. He developed this concept in his day. Currently, he is a educator at the Institute of Basic Science in Korea. The presentation will be around 50 minutes and 10 minutes for discussion. And I encourage you all participants, especially students, to actually ask questions to the speaker. And also special request by Dr. Šafránek. If he has a question during the presentation, we can really ask the question directly and discuss it during the presentation. And without further ado, please, Dr. Šafránek, it's time to start.
Hello. Yes. Thank you for the introduction. I'm going to keep it simple today. So the basic thought. It's also good for me because some research I don't know much detail. Okay, so I'll talk about entanglement and explications. Very basic ones. What I'll talk about is first some kind of just the first notion of the reason it's entanglement. Probably you've seen it the last few days already. Then I got a bit about the spooky action at a distance. I present you the definition. Then I'll talk about this difference between entanglement, correlation, and some other quantum states, namely quantum discord. I'll introduce for inequality. I have that some of you already see this on Wednesday. So if it's too much, please let me know. I'll discuss about faster and speed of light communication through entanglement, whether it's possible. But this, as I mentioned, and some applications. Specifically talk about first. On protocol is computation, which by itself is not very useful, but in many simplification is very useful. So what is qubit? You have a bit called it, right? So one simple bit is either 0. The possible bit is either 0 or 1. So it's either on or off. But the qubit is something different because you have 0 and 1 and between. And anything between 0 plus 1 is 4 0 1. And entanglement is a superposition among multiple qubits. So when you have 0 plus 1, it's so 0 plus 1 is not one of these, so it's certainly in between. And if you just take this superposition, but you have a multiple qubit space, then this is called entanglement. So entanglement is just superposition of qubits. And here I can just something that we do not know. So the protocol is completely. And these elements of reality are today no longer domain of hidden variables. And of course, because in the early age of mechanics, representative generally, Skyhouse, they are all they talked about, the language they talked in about quantum physics was German. So he named this language that we use the name of Version Group, which is not the redundancies in English, and it was used by English in order to understand. And also later, Einstein was saying that entanglement violates the speed of light, which violates the special relativity. That's why he eradicated and said it's nonsense. So he eradicated entanglement as a spooky actually distance. So what is entanglement? Let's start with the definition. Consider two parts of the system. You can say part A, which is partless, part B, which is part and you have some bases. So you can think of this as like 0 and 1, but there can be also 2, 3, so here as well, so 1, 2, 3. For pure states, the definition is relatively simple. Because any vector you can write in the basis with these sectors. So since the product basis of the geometrical vector space is given by this vector times this vector which is this thing, then any other vector can be written as a combination of these vectors. So this is always possible for pure space. But if you can write that this psi is a product of two states, then we see that the state is an entangled, it's a product state. So anything that cannot be written this way is entangled. So pure states. For pure states, the definition is more complicated because you have invariant matrix, which maybe some of you know, some of you don't. Let's put it this way. If you have density matrix of the full system, that can be written like this. So this is a probability distribution, and this is some density matrix of the first system. This is the density matrix system. So you can think that this is a separable state. Separable means absolutely no correlations. So if you can write this state as a classical mixture of product states, then the state is also product state. And you can imagine also if you have the K and K and K are the same case. That's how we want to so if the state cannot be written in this way, then it is called a state. Of course, this is much more complicated definition than for pure states, and it's not generally easy to find that the state is entangled than the states. For pure states, it's easy, for the states, it's not. So let me give you some examples. So this state I guess it's so also we get right. So this one is entangled because no matter what you do, you like this. This one kind of looks entangled on its own because you can vector this 0 out. So this is not entangled because you can write as the 0 minus 0 plus 1. And I mentioned before, this much harder. This first this one is shown by the in which order this is written, so it gets to the first step, and the superposition will be this is 0 at focus 1, and this is 1 at focus 0. So that is again, that's the normal and focus 1. So let's take this entanglement state. And when measuring an computation basis, we have perfect correlations. So that's in computation basis, when we measuring basis is 0 and 1, then there's perfect correlation. So let's say 0 on H is 0 on 0. Then the state collapses into 1 because the state is not there. So she measures 0, it means that 100% chance for correlation. If we randomly obtains the outcome 1, then the probability is 0. It's something like in classical you can also get perfect correlations in classical physics, and the example is just pool. So for low resolution is very dependent. But in pool, one feature of pool, at least one variation of pool, is that the white ball and the colored balls are the same weight. And if you remember your high school physics, then if you have the balls of the same weight, then when they hit each other, they always go away from each other at the angle of 90 degrees, always. If they have different weights, then the angle depends on the weight, but if they have the same weight, then it's always 90 degrees. And that's why this game is not that difficult to play, because it's highly predictable. If this ball was slightly lighter or heavier, in some measures of it's much more difficult, because you need to take into account, the angle and the weight. But this way it's very easy. So you play this game, you know that you don't practice too much to get something. And here it's basically also perfectly correlated. What I mean by that is that if you take the white ball and you hit some other color ball, this blue ball here, and then you just measure the angle by which the white ball went away, like this way. Then you can predict with 100% chance under which angle this ball goes in this direction, because we are 90 degrees angle. So yeah, classical perfect correlation. So just because you perfect correlation doesn't mean it's quantum, but it's quantum for a different reason. And that's because in quantum physics we can change the measurement basis. So even if you measure in computation basis, you can measure in plus minus basis, or C minus basis, where you have this vector plus, which is a superposition between 1, and the vector minus, which is superposition between -1. So with this state, with the same state, if Alice chooses to measure these bases, and she gets a result plus corresponding to this state for system A. Interesting how it works, Bob will also always get a plus if he also chooses to measure these bases. And if Alice obtains minus, then also obtains minus. So they are still perfectly correlated, even though they change the basis in which they measure. And this is something new, right? Because in classical physics, you don't have these properties. It doesn't exist. Even with slide or wave, right? There's no such thing like 4 or something like 4 plus 4. So this is a little bit different. And this is also been formalized by Bell first, and then by some other people in this CH station quality and next. has access to this first qubit, and the second L is 1. And they can make different choices of measurement bases in which they measure. So imagine that the choices are either like computation basis, which is this one, or cross lines basis, which is this one. So analysis can choose this A or A dash, and both corresponds to B or B dash. And classically, will be possible if you have some local variables, meaning what I'm saying calls like mixing zones of reality. Then this function, which I'll explain in a moment of this, if you take this, so then it must be always smaller or equivalent to, but as it turns out, it's not. So what is this function? It's some kind of function of correlations. So this, let me explain what this function is, because I already said. Or maybe, okay, let me explain this one. So imagine that Alice chooses to measure in A dash, and Bob also chooses to measure B dash. So Alice can get either outcome plus or minus, and Bob can also get outcome plus or minus. So if you calculate the number of times that both Alice and Bob got both plus, this is that n plus plus, and you subtract when Alice got the number of times that Alice got plus and Bob got minus, and Alice got minus and plus, minus. Just copy these numbers. And you do this with all the choices of different bases. Then you can compute this quantity, and you can get that this function is 2 times square root of 2. So you can see this E corresponds to different yeah. This last one, okay. No, I mean, okay, it proves there's no local hidden variable theory. There are some non-local hidden variable theories that are still possible, which that is some like consonants be the right match for some sort of application. But this is a statement instead. What do you mean by hidden variable? Oh, I see what I mean by hidden variable theory. So in quantum physics, if you measure some observable, you get outcomes at random. Right? So you can choose the setting for the detector, which is you can choose the basis which you measure. But you cannot choose your measurement outcome. So you can get the plus, let's say 50% chance times 50% chance, sometimes 100% but you don't know exactly for sure. So in classical physics, that's a little bit feature because there is probability that you measure something. You will get the outcome with certainty. Just like I ask, where is the particle, where is for example, I see it. I don't have options. I see it here, 100% chance. But in quantum physics, it's not like that. You can say you can measure something in somewhere and just so there's some probabilistic nature and Einstein believes that because there's probabilistic nature, there's something we don't know that the algorithm is complete because there was something that you do to measure these hidden variables that I didn't actually measure. Then our theory would be deterministic and we would be able to get the right answer every time. As it turns out there's no such a thing. So there are no hidden variables that the next study is saying the account of the So yeah, Einstein was nothing there. So Einstein was one of the people that actually started So, entanglement is strong form of correlation. What about the second question? Does it break speed or what? After all, it's against actually when you measure some the collapses state. Whatever by collapses related to this state. Said, all right, how this gets measurement of plus and plus. And this is the thing is. Yang says no. Why is no? There's another theorem which is called no signal theorem, or also called obligation theorem. And it says that if you have two subsystems, subsystems and both subsystems, then no matter what analysis does to have part of the system, both will not take difference. And this is a bit surprising because I just said, oh, if analysis measures plus, then for all also measures plus for sure, the base example. But that's only if that's in the knowledge of others. It's not in the knowledge of all. So if Alice measures plus, then she knows that it also measures plus every time. I hope doesn't know it. So locally, if Alice doesn't know all, the hope is still uncertain. How is it described? Well, if you look at the local subsystem, and that's given by the local density matrix. Let's say you take a look at both subsystem before the measurement. So you are taking partial place on the full system. Then you get some density matrix. But if you look at after the analysis made the measurement on the local subsystem, you're still gonna get the same density. So Bob doesn't see any instantaneous change in his system. Alice's system happens because she operates on information by the measurement. But unless Bob knows this outcome of the measurement, or it's going to be limitations. So this can be summarized that just the measurement of the coordinates cannot transfer information. And what is this derivation of that? Well, it's basically a sort of proof of this theorem, and I use some measurement device, and I extend the device space by one other subsystem C. And the measuring is measuring is basic the interaction between the subsystem and the measuring device, which is called the spin plate, and then the cycle the device and the subsystem. I don't know too much detail because so there is no taking on this field. So there's a second part that comes out. And that's the third problem of physics. So the conclusion is this section, entanglement is a form of correlation, somehow stronger than positive correlation, even stronger than perfect correlation. But you can have perfect correlation not in classical physics, but if you want to change your measurement, this is not this we can get strong correlation. Yeah.
You said that there is no transformation of information with after that. Like the reason that we collect on the state is not visible.
Yeah, exactly. So there's really this because the collapse only happens just in your mind, in your intelligence. So Alice measures something, she gets an outcome, and given this outcome, she updates her information. how she feels about the system. But the same thing, like you call your friend, where are you? So before you call your friend, where are you? You didn't have clue where she was. But when he tells you, you have the information, so you suddenly know where she is. So there's a thing in your mind. It doesn't affect your friend because the friend knows where he is, right? But you didn't know it.
The reason said that one mechanic does not full physics, but full information.
Yeah, when it comes to measurement, it's really a question of information. So let me continue with an example, right? So if you have another friend, just because you called your friend A, and you now know where your friend A is, it doesn't mean that your friend B knows where the friend A is. From the point of view of B, nothing changed. So it's really, the measurement is just really updating your information, not the practice information. So the column still is a way how to update the information that you have about the columns. So I can summarize this point that the columns of the wage function is a result of updating your information about the state by the means of you interacting with the column. So what is not entanglement? As we said, separable states are not entangled. Even though those can be correlated, but they are they can be correlated classically, but they can also be correlated on at least and this is supercomputers. Next, which element? So maybe so what's the difference between entanglement and quantum discord? Entanglement is really a result of two different systems interacting with each other. So if you have, let's say, a system A, system B, and they just hit each other, so this is a one particle and one hit each other, you can get some entangled state from the other. Quantum discord is a type of correlated state, even one correlated state, but which is not entanglement. And you can eventually take when I'm let's say I take a point, every time I get heads, I will prepare state up and up, two states. And every time I get tails, I will prepare a state horizontal and 45 degrees, so it's out of this continuous as possible. And if I'm going to send these particles to somebody, in the audience, let's say we describe the system as a classical mixture of these two. So this state was created by me throwing a coin. So there's nothing fun about it because it's either this state or this state. But whoever I'm sending this to, they don't know what the outcome of my throw. So this is the way they describe it. It's a description of the state that probably somebody doesn't know the outcome. And this is some kind of state that's correlated, but it's so what's the difference between entanglement and this? This is that entanglement is useful by the correlation. Let's just know this. So for the state to be entangled, the values must have interacted in the past, or they must have interacted with something that had interacted in the past. It's also translate that. So this is the case of states. Some uncorrelated states, which is like this, several states. Then you can classically correlate it. This is an example of a classically perfectly correlated state. Perfectly means that if I measure, let's say, spin up here, then I know the certainty the body also measures spin up, but it's going to fly. I know exactly it's possible to be positive. But there's no entanglement in this. You get found this board, so you can see that there's different some of the states that are and then you can have stations. So what's entanglement is useful? Entanglement is useful. Meaning can be used to study it. And useful studies on location, cryptography, computing methodology. And there's also a field of this. Yeah, maybe I say this. So how is entanglement used in computing? There are some known algorithms, the most famous ones is short algorithm and close algorithm. Short algorithm was really a game changer because it was the first algorithm where the quantum computer provides an exponential advantage. Meaning that if you have the size of the problem, let's say there was a size of the problem, if you have some number, you want to factorize, and the size of the problem is the length of the number. Then using Shor's algorithm, you can factorize it into prime numbers exponentially faster than any possible algorithm. And Grover's algorithm is for finding an input from a set of inputs that this is the exact output. So Shor's algorithm is earlier the question is I have a big number and I want to find its factors. And Grover's I have some function and I want to find an input x that gives me the exact output y. And entanglement of these two systems are used in both cases. So in Shor's algorithm, there is entanglement created and entanglement to a distance, which is some distance. And then we're performing non-Korean transform, which is here at NSA study session with that. There's also application of confidence and simulations, which is not exactly related to an end state directly, more the smaller statement that if you simulate some landings of landings. You can do this efficiently across the So how does quantum computing work? Just to give you maybe some intuition about it. It uses constructive and destructive interference. So you probably very well know this double-slit experiment. Then you have some photons, you can do electrons, and they go through a double-slit process. Here, once they go through, you will see an interference surface behind. So this is called interference. So if I move it here, this is how it looks like. You have some kind of paths coming from the first slit to the second slit, and you get these stripes here. That's because these paths interfere and but on a network, on a quantum computer, this means logically integrating the many paths. And then that's the sort of advantage that the quantum computer is that you can go through every possible part of space, whatever space is. And since the wave function explores many different paths, you can call it functional information using computing and quality. do some output that's useful. So if you did not adhere if these photons acted as just positive particles, you would see something like this. That's what we see this. So this is what we are using. Let me give you another example of this interference, how it works on creative systems. So that's a quantum versus classical walk. Classical random walk is some sort of a game. You say, okay, I throw a coin, and every time I get tails, I'm going to go to the right, and every time I get heads, I go to the right. And then I explore randomly this space. So I throw a coin, I go left, I go again, I go left, throw a coin again, I go right. And it happens that if you do this, on average, you will still stay in the middle. So this is your current distribution. And the range, the second division will go with this variable number of terms. So it's going to be this. Now, in quantum physics, something is different. So if I throw something called quantum coin, which is, you can think of it as a gate, so let's say I can see where the light go, depending on the outcome of the throw. I'm exploring basically the blue space, and since I'm not quantum particle, so my measures in the amount of so, and what can happen in this case if you choose some very specific quantum core within the gate, is that you can get a very different pattern. You can get a pattern like this, which maximizes the probability I'm going to be in the size of this radical. Probably I will be, and it's not also possible. And this is the essence of computing. I mean, it's choosing the interactions of these gates in such a way that I get the desired output, which would not be possible by having all these different trajectories interact and create some very nonsense behavior. And this means that they can touch all the possibilities faster than anything else. And they must interfere to get a sense of output. And then they have to be small in a way that in the end you just want the main function to just you want it to just appear like non-zero on some small part of Hilbert space, and from that you can measure the provisional outcome and determine the answer you will get. But if you get if you get a very large output, meaning that it's like an elementary values very useful. So depending on the main function that you are measuring, you can get some outcome from that. So example of the Schwartz algorithm, and definition here. So the Schwartz algorithm in a nutshell is you have some large number n that you think is factorized by the standards in Q. So it's a and normally what we do is, okay, yes, it is a I'm gonna guess that G divides that. And this is never a bad guess. And it turns out from some approximate analysis which I don't understand, apparently a better guess is whatever G you choose, the better guess is G to the power of R over 2 and plus or minus 1. So there are two better guesses. If, and that's it, if you manage to find this R, which is some integer, such that G to the power of R is some product of N, which is the original of plus 1. And apparently, there's also a theorem which says that this is always possible. So if you can measure such R that size is okay, then this better guess is this of N in about 37 times another basis. So because of this, I guess it is a bad choice. But if I take some powers of R, I may take power 2, like 1, 2, 3, 4. And at least that's whether the power can be anything like this. Then I'm going to find R, and this is a much better guess. However, finding R is a very difficult computer, but it's not a quantum computer. So this is just kind of standard mathematics, nothing comparable with R. But it just says that possibly this R is still defined. But short algorithm is based on this part of the algorithm actually easier. So in works, you have two parts of the system, this X part and this H and Y. You apply some other market on this X part, and then you apply some entanglement gate. And this looks like this. This X goes over integers, so 0, 1, 2, 3, 4, and so on. And if you apply this gate, then you're gonna take an entanglement state of X and A to the power of X. And A is actually a G in this case. And So you create some perfectly correlated state here, and it is modulo as n, so you just take a remainder of this. I need to use some other quantity for quantity transform, and we measure probabilities sometimes on this we can somehow infer this R. So how does this work is that it's very difficult to find R logically, but if you do this procedure, because it goes through many different trajectories at the same time, somehow, using this magic, I can get from measuring this part of the right R, the closest problem, the polynomial time. So once it is the exponential time, how to do it is going on. That's going on. We also algorithm that is searching for all possible inputs such as the function value is and with that I'd like to conclude. So entanglement is a measure of correlations. Entanglement are those correlations that are useful. It doesn't violate the special kind of relativity compared to Einstein set. It excludes existence of the local indeterminate, and it has certifications, namely propagation if the vector incomplete, which is quantum resolution on properties. And in quantum computing, the advantage comes from non-selective and distractive interference by which allows the search for many possibilities.
much for the talk, Dr. Šafránek. We welcome some questions from the audience. Yes, please.
If you go to your presentation, I would like to ask how can we take the data or the company's work or because I think there are people that is one of the results for what we did. And it is possible to have, for example, maybe more explanation of where environment is going to work. Is it possible to have environment impact on the work or
Yeah, I'm not so convinced about this convenience source. I like this. I'm not sure it makes sense. But I can talk about the other part of the relation. Maybe I can just give you an idea of why I don't think it's useful of maybe zero services. Why I don't think it's not very useful because this slide is that there is nothing on this state, like this part of the state. And there's nothing on this part of the state. And because ultimately, if I know that there's an outcome, I know in which state this is, but maybe if I say you really know which state it is. So for me, it's certainly not useful because there's nothing quantum about this. I'm not really sure maybe there's some usefulness in the fact that somebody else does not know. But I can tell you more what is maybe about the second question. What is the entanglement discord? So discord is form of correlations. And it's not in the following sense. So it's a correlation in the following sense. So in this case, if I measure spin up on the left part, there is 100% chance for positive spin up. But if Alice measures spin down with current line, only a 50% chance for measure spin up and 50% chance of spin down. Because this is supported. So this is not exactly symmetric. And I can play this game, again with information basis. So I get perfect correlation between these two, not perfect correlation between these two. What's different between classical correlation and quantum discord is that you cannot distinguish quantum discord from this classical correlation if you don't change the measurement basis. The quantum discord states, however, they have the feature that the eigenbasis is an entangled state. So you need actually a measurement entangled basis. You do not need entanglement in integration, but you need measurement entangled basis to identify the quantum discord. Because there was nothing was ever entangled, it was just stayed like earlier. Yeah, does that answer the question? So you have some additional.
One question? Yes, please.
Thank you very much for your presentation. How about the application that is better basic? Firstly, we make sure that I great basic. You said that quantum entanglement is a correlation and not an action per se. It's just like basically it's the law of information of momentum energy in the
first question, and I will wait for the last one. I was since it's a form of correlation with the power accumulation relation. That's a good question. Well, there is no such a thing as conservation of entanglement. So it's a form of correlation that specific way system. But you can say entanglement, usually one of the definitions is as a entanglement, such as entanglement entropy. It says that entanglement entropy is conserved under so-called low-season operations, which is any local operation we can do on a subsystem, and then possible communication that you can do with partners. So you can imagine I perform any gain on subsystem A, then I measure anything on subsystem A, then I send the outcome of the measure to log. The number of measures should not increase If I measure, I can disperse entanglement. But if I do locally unitary, I don't have entanglement. So yes, there are some operations that if you restrict yourself to those, then you can say think of entanglement as a consequence of because you can create entanglement. So do you mind me to yes, of course, yeah. That's around these slides. So a mixed state is separable and we write it like this. And then in these mixed states, you cannot write like this, then it is entangled. So an example of an entangled state is, let's say, you have very very close to 1, let's say 1 minus epsilon, and this part here is this maximally entangled state, which like this one. So it's predominantly maximum entangled state, but there is some small input, let's say non-entangled state. So there will be a big state that's entangled. Because you cannot write it like you cannot write it like this. And when it comes to mixed entangled states, there are also some measures of entanglement. They are much more difficult to calculate. One of the easiest is related to productivity. There are also other ones that are fundamentally more important, let's say, so entanglement correlation. It's still difficult to do. So for instance, it's very difficult. Will you answer the question? Well, they communicate through, if they need to communicate in this sort of process, usually there's a positive information. But you can also say, okay, if I perform some entanglement gain, it's also a communication. But entanglement gain means really I draw those two systems close together and I let them interact. That's the point I was trying to make. So this is basically communication between A and B. And it's the same thing as with the pool. If you have these two balls in the middle, one ball, it hits the other ball. That's interaction. So let's say it's correlation, classic correlation. We want to take the data down. So we can just go for some sort of communication. Sorry, so classic communication. But then we can say that for the classic. More question? Audience? Yes, please. entanglement becomes. So the future of entanglement is that something interacted with the past, some entanglement was created, and if it stops interacting, then the amount of entanglement these two parties does not change. It remains constant for the rest of the universe. You can undo the entanglement again with some interaction. So you can imagine like you have a particle here and a particle here, they interacted, they become entangled, separated. So they are entangled forever. Or they can go back together and interact again, and they can still entangle. Or they can interact with something else, and then something else transfer the entanglement to something else, and then something else can go back and interact, and then also still entangled. But you know, it's always either created or destroyed through interaction. But this is like ultimately like if you consider all systems would be like in the universe. Sometimes you can call interpretations that like everything is unitary ultimately. But if you consider all the subsystems, then yeah, you can destroy entanglement. And that's because that's what you do in the measurement, basically. So example. This is the example where we describe the environment. So we start with a tangled state, and all is measured in the computational basis. And let's say she got measurement 0. And because she got measurement 0, the state was projected onto this state. So this is a two-body state. So it's like state 0 on analysis part and state 1 on both parts. And it's not entangled because it is a product state, right? So there's no entanglement. So you see, she destroyed the entanglement of the subsystem. But was the entanglement being actually destroyed? No, it wasn't. It just, what this mechanism did is that in order to get this outcome, she had to use some measurement device that interacted with this subsystem here and became maximally entangled with the subsystem here. And because it became maximally entangled, it just transferred the entanglement from between these two qubits to the qubit of both and the measurement device. So in reality, the entanglement was not destroyed, but it was transferred from the subsystem A to the measurement device. But since you are ignoring the measurement device, it appears that the state is no longer entangled. So there's this connection in many worlds, right? Because ultimately everything is entangled, but if you look at the subsystem, it might not be. Dr. Arno, please, question?
So, thank you for the talk. My question is, in the real experiment, usually we should consider the temperature dependent. We should consider the temperature dependent in the real experiment. For example, in the production. So how it affect or how we include that temperature dependent the system will encounter.
The temperature dependent?
Temperature dependent.
You mean like when you're creating entanglement, where does the temperature appear?
Yes, how it affecting the encounter.
Right. That's a good question. Well, in terms of the system in which you want to take entanglement, right? So, creating entanglement with, let's say, between photons and the temperature is not almost doesn't play a role. So we have these value or crystal, which is those that will parametric down conversion. So you shine one highly energetic photon into a crystal, and about 0.01% chance. And entanglement state between state so that the high energy photons transfer to low energy photons. And they are maximum entanglement is also visualizations. And here the picture is not very much of a role because you can do it with illumination. But if you let's say have superconducting qubits or complex, and there are some initial calculations. But I think in that case, it depends on the specific way you manage to program the system. So ideally, you would like to start this, let's say, all state being zero state, and then create some interaction between the two zeros, and out of that you get an endemic state. But as you all know, the certain rank law prevents us from reaching it to zero. So you cannot ever get down to zero, so this is something which is side. Basically means you are very close to zero, but you are in a endemic state. It's not a condition. So you need to make some sense. You can pull down properly, so then you get close to zero. But you'll never reach the zero, and then if you take the applying this like a gate, then this energy will propagate. So there will be always some part of mixedness.
Okay, so we came to the end of our session. Please give one more applause to our speaker. And this session is coffee break session. So we have the coffee break session until 9:30, and we start the next session. So see you again on 10:30.
Oh iya iya.
Ada dicoba.
Jadi ada tol yang sudah digabung.
Shall we start the session? You think? let's do another minute. I just want to remind everyone to let's start the session. So, thank you very much for staying with us. It's a very nice day. This is a workshop. My name is Entanglement from BRIN, and I'm happy to share with you the last remaining sessions today. So before we begin the presentations, let me introduce our speaker, Dr. Hongyang Zou. I hope I pronounced my name correctly. Forgive me if not. So he is the vice, as you can see here on the slide, is the vice president of SpinQ Technology Corporations, established in 2018, based in Shenzhen, China. He got his PhD in physics from Washington University in St. Louis, right? And then prior to joining the company, he worked mostly in the field of Alexander physics, raising nuclear magnetic resonance state. So today we will introduce us to the superconducting and NMR-based quantum computing and what the company has to offer. And without further ado, let's welcome Jude.
Thank you. Okay. Hello, everyone. It's my pleasure to come to BRIN. Today, the workshop topic is here, the introduction to superconducting quantum computer and the nuclear magnetic resonance quantum computer. I'm Dr. Zou, the Vice President of SpinQ Technology, and now let's begin our talk. So what are we going to talk about today? In today's discussion, we will start by addressing two fundamental questions. What defines a computer? And what characterizes a classical computer? And after establishing these fundamental topics, we will delve into the concept of quantum computing. This will include the overviews of superconducting quantum computer and the NMR quantum computer. We will focusing on the hardware aspect and the operation methodology. Then we will engage in an in-depth analysis of comparison between the classical and quantum computer. Okay, first, what's a computer? When it comes to a computer, the first thing that comes to my mind, I'll be using a calculator and calculate some complex multiplication. But indeed, it's much more than that. Okay, the essence of information processing is computing. BRIN is the earliest tool of computing. It computes all the time. For example, it's computing when we play chess, play mahjong, or choose the teacher color, or decide what to eat for the lunch today. Or BRIN naturally from abstraction and computing. We may use some tools to help us with computing. It doesn't matter you are using your finger, the computer, or the iPad, or a supercomputer. The invention of the classical computer has improved the level of computing and information processing in all walks of life. And later we will see the quantum computer is also another tool for computing, but even better and faster. Okay. Have you thought about what classical computer really is? We are using it for study, for work, for entertainment. It seems we are using it for everything. Let's see the history. About 300 years ago, we have the innovation of binary logic. And 200 years ago, we have the mechanical computer. And about 100 years ago, we have the electronic computer. Regardless of materials, if the basic components can express two states, and the space between the two states, and we can transfer the states to some other basic components, then they can be used to realize logic circuits and logic gates. Once the logic gates are implemented, building a binary computer is as simple as building blocks. Okay, the Boolean operation are logical operations used to manipulate and calculate the two values. The basic unit of computer operation is the logic circuits. There are three basic logic gates here. AND gate, OR gate, and the NOT gate. Here are the truth tables for all of them. And when it comes to the underlayer hardware, then we are talking about this metal oxide semiconductor field effect transistor, which is used to control the current or function as a switch. When this VT here, when this VT is at high voltage, then this S and E, they are connected. The transistor is the fundamental component of modern electronic devices and digital circuits. Okay, so what's the relationship between the transistors and the logic gates in a classical computer? Here is the relationship between them. For example, this AND gate here. Here is the table of AND gates, and there is the circuit diagram of it. There are two transistors here, this one and this one, and the input A and B here, both of them, they are at high voltage. Then this transistor is connected from top to bottom, and also this transistor is connected from above to bottom. So this output port is connected to this 6 volts power supply. That means the output is at high voltage. So the result is 1. Otherwise, if one of the input is at low voltage, then that means this output is not connected to this 6 volt power supply, but is connected to the ground. So the result is 0. All logic gates are based on circuits with transistors in classical computer. Now we have the logic gates. What are we going to do with them? We have to use is to solve some problem in our labs. Otherwise, they are just some very beautiful. Here is an example. The half adder, and here is the truth table circuit, and the logic circuit is here. We combine this blue array and this aggregate here to achieve this kind of half-adder logic. And now, finally, we can use a classical computer to do addition. Okay. Now let's move on to the next chapter. We have talked deeply about the classical computer that we are using daily. Let's think about the superconducting quantum computer. We have many ways to build a quantum computer, including using M-trap, nuclear magnetic resonance, photon, or the superconducting circuits here. Among various quantum computing hardware systems, superconducting quantum technology utilizing more stable or solid-state system. It's easy to manipulate, couple, and read. Well, it's also allowing the free use of the mutual semiconductor processing technology. So it's considered one of the most promising routines. Consequently, it has become a focal point for many companies, include us, many other big companies, and also for the research institutions. So here is the architecture of the superconducting quantum computer. And we use the quantum chip EDA, scan over chip, and then we dive the chip in the room. Then we put the superconducting quantum chip in the dilution freeze, which will allow the chip to work at very, very low temperature, about like 10 millikelvin. And this will ensure all aluminum is superconducting, and the qubit will not go by state because of the heat. Yeah, Dr. Also talk about this part yesterday. Okay, now today we can look this kind of superconducting quantum computer from another aspect. Okay, and then we use this measurement control system to send out and receive that kind of code to 8 gigahertz radio frequency signal to manipulate the qubit and read out the state of the qubit. And finally, we use our classical computer to connect the user and the hardware itself using the computer, desktop computer, and connect the quantum computing application level and the management and control system. And here are some real photos for quantum. For example, the quantum chip fabrication lab and the photo on quantum chip and their microscope. And here is the whole machine, the whole superconducting computer, and over here is the measurement and control system, a unit, a draw of the techniques. And here we take out the arbitrary wave generator motherboard out. And what can we use it for? We can send out any signal you want. Here we send out beautiful on our oscilloscope. And there is a reading. That's how it was designed the first. Except the dilution cooling units, we have many low temperature electronic devices in the grid, like the low temperature amplifier, circulator, filter, attenuator, and so on. In recent years, the performance of quantum computer, especially the superconducting quantum computer, is improving quickly in many aspects, like the number of qubits. It was 433 last year, and just a few days ago, in 2023, it's already 1,000 qubits right now. And also, we have big improvements in the fidelity of communicates and also the lifetime of the qubits. Okay, and the heart of superconducting quantum computer is the computing. So let's move on to this one. If you want to have your own quantum chip, then open IDEA and then you chip might be the first step, except that you want to draw the layout by hand. We have completely bypassed the EDA on our cloud, and we did it anytime you want, and it's free. You can, and then let's have a look what's the interface of this online EDA. So firstly, it's completely web-based, and you can have access to it anywhere through the internet, and we have rich rich components library. So it's can add on some XC1 here, and there is your friendly interface here. And you can use parameters to design your qubits. You can draw that qubit by yourself. And in the end, you will see it can automatically vary connect the qubits to the bottom height by the software, by the EDA itself. Then you want to draw the line by yourself, especially when you have many qubits, like 50 or 100 qubits, then this function is very useful. Now I love the line. After we present the chip, after present the chip, next stop is going to the silicon and the back of the chip.
Designed for on-chip aggregation. Silicon and sapphire are commonly used wafers in quantum chips to down superconducting quantum circuit. A layer of superconducting metal field is brought onto the wafer surface. A layer of photoresist is then applied on the field. Based on design pattern, specific areas are exposed to laser light, resulting in changed properties. The exposed photoresist is dissolved and removed with developer solution, followed by etching the exposed metal layer to form the surface. After rinsing off the remaining photoresist, the surface is revealed. Next, we apply 2 layers of electron beam resist to fabricate a Josephson junction circuit. EDL is employed to define an area for the Josephson junction circuit, which is formed in a cross-shaped area. A specific technique called double angle evaporation is used to create a superconductor insulator superconductor 3-layer structure, allowing superconducting metal to grow only in specific groups. Between the 2 evaporation processes, an oxidation step is introduced to create the nickel oxide layer. From the side view, the 3-layer structure of the Josephson junction circuit is visible. Excess material is then cleaned away using a resist remover. Finally, we get a wafer containing superconducting quantum chips.
Now, our customer available solely series company chip have up to 20 qubits, and the modern microprocessing device and the single fidelity is higher than 9. Now let's move on to the next chapter. Except the quantum chip, the most most important part of the superconducting computer is the measurement and control system. We have many modules included in this system. For example, the arbitrary generator, the quantum analyzer, actuator, the Doppler distribution unit, or trigger distributed unit, and something else that's necessary for the system. And here is an architecture of the measurement and control system. The chip is here. We connect the measurement and control system to the chip. The chip is in the freeze. Measurement and control system is in the room temperature. And we use our AWT, the arbitrary wave generator, to send out direct current, or we sometimes we also say the flux or the bands. That will goes into the chip, show the data. We use this signal to tune the frequency of our qubit. So this is the tunable qubit. For example, it's at 4.5 gigahertz. Then I use this signal through this data. I can change that to 4 gigahertz, or I can leave where I want. And then we use this AWT send out something like 1 megahertz or 200 megahertz signal, and 1 second, 1 2 and using the feature to mix with the high frequency from the microwave generator, for example, which is like 4 gigahertz, and then we will have the signal that we want for the 12 line. The 12 line also called XY line on the chip. We send in the signal going through this line usually between 4 to 6 gigahertz, and this signal is used to change the state of the qubit. For example, initially it's 0 state, and then I send a pulse through this XY line, and then I will get 1 state of this qubit. And after this we also have the reading and without that here. The reading part is similar as the value. Also, AWT send out I and Q mixed with the microwave and send in the signal. But this signal is usually like between 6 to 8 gigahertz. And then the signal passes through the transmission line in the chip, and it comes out. Then we demodulate it to about 1 or 200 megahertz. Then the signal goes into our quantum analyzer. We analyze the result to get the result of the qubit. So we show on our classical computer to communicate with the user. And now let's introduce some components of the measurement and control system. For example, this one, the arbitrary generator is AWT 1208 has 8 output channels, sampling rate 2 gigahertz, and vertical resolution 16 bits, and has bandwidth from DC to 400 megahertz. And also it has good synchronization. Here we send the signal on the oscilloscope. So they have good synchronization channels. Okay, and there the quantum analyzer. They have 4 channels AWT and 2 channels of activation for ABC part. And the AWT part is the same as last page. The activation part, we have like 1 gigahertz sampling rate, 14 vertical resolution, still 400 megahertz video frequency bandwidth, and the synchronization is still the same. Also, we have some other components here, like the accumulator. They can work between 2.5 to 8.5 gigahertz, and has local peak suppression, both the and the image detection. Also, we have this log distribution and figure distribution because we have many qubits and many units in our system. So we need to make sure all the units work at exactly the same time to make sure the flow is very accurate. And here are some unique features for our control system. For example, we use as computing technology by FPGAs instead of using CPU. We have so many FPGAs in our system, and the FPGAs they can run faster compared with CPU, so it will lead to a faster measure and control, and also the synchronization and the workflow execution will make sure they have good accuracy. It will make sure that you have like the more than 99.9% single fidelity, something like that. And also it's convenience to the customer. More than 100 bits. We have the monitor system. For example, if the accuracy is not that kind of good, you do need to get the system apart to have a check. You can check that directly through your accessing database, and also we integrate some function like the DNA, the network analyzer, or the network working in our system. This will save lots of money. Later we will see usually people like to use the network analyzer to scan the cavity, and we can use our systems and the cavity as fast as DNA, but cheaper version. Okay, here let's move on to next section. Now we have the chip, we have the measurement and the control system. What's next? Next is we use our measurement and control system to measure and control our qubits. So firstly, we sweep the frequency of the resonator. You can use a DNA or something outside similar in the measurement and control system to measure the ISQ1 of the transmission line, or you can also say the readout line. Here we can see 5 cavities between 7.5 to 7.7 gigahertz. This means we have 12 qubits on this readout line, and later we will show you they are the pair cavity. That means we do have 5 qubits here, but the qubit state change from 0 to 1. This kind of line won't change. Now we sweep the frequency of the resonator again and again, but with lower and lower power. This is what we get on this graph. About minus 20 dBm is the pair cavity, and below minus 30 dBm is the, we call it dispersive cavity. The frequency of this kind of dispersive cavity here. It will change when the qubit change from 0 to 1, while this pair cavity will not. So the dispersive cavity is what we want. From here, we know this dispersive power that we are going to use for all the experiments, all the following experiments. Okay, then we sweep the flash voltage, or say the direct or the bias voltage. Then we try to find out where is the sweep point. Usually we use like here or here, from here. Then that compare with here, if it's more stable, your flux voltage change like 1 microvolt, then you here it's more stable. And compare with the when the qubit from the frequency, then it's very near the bare cavity, so you cannot tell whether it is the cavity when the qubit is at 0 state is equal to 1, and then if the qubit is at 5 state, then you scan the cavity, you will get this origin one. So this is how we measure out the final results. In that usually when we do our experiment, we don't need to measure the whole cavity spectrum. We just need to look at the this one on the TV. This one. I always look at this frequency. If the qubit is 0, I will get this dot, only one dot. And if the qubit is at 1 state, then I will get a dot here. So the amplitude has a big difference between them. So I can tell whether it's 0 or 1 of my qubits. Okay. After this, you will do the qubit spectroscopy to manipulate. We need to find out what's the frequency of our qubit. Then we will use that qubit. We scan the. This is the cosines. We scan the frequency of this 12 signal. For example, here we scan from like 12 gigahertz, 12.09 gigahertz to 12.11. When the 12 signal frequency is different from the qubit frequency, we will get nothing. The qubit is always at 0. It won't change. And then we look at when we drive it at the qubit frequency here, it will move up. If it is not one state here, 0.5 up, 0 up, one state, but we can still tell where what's the qubit frequency from this one. And now we have the qubit frequency. What are we going to do next? We will do the Rabi oscillation. For example, here we change the pulse length from 0 to 600 nanoseconds. When the pulse length is always at 0. So here when I do a pulse at about 50 nanoseconds, it moves up to here, then that means the state is 1. So I know like the IXK pulse length is about 50 nanoseconds, and then if I do it pulse longer and longer, it comes back from 1 to 0, from 2. Now, like the qubit frequency, we know how what's the pulse length that we use. I want to give it I state, and then we can measure this kind of one. How we measure it? We first give it measure it. If I wait like 0 nanoseconds, then the qubit is exactly at 1 state. But if I wait long enough, much longer than the lifetime of the qubit, then finally the qubit always will go back to zero after 3 or 5 even time comes back. And here we would like to measure the T2, so we use 2 poles and we change the delay between the 2 poles. We got this kind of 20 spectral, and we can get the T2 values through this measurement. And after this, we can do the RPI, the single qubit random benchmarking, to get the fidelity of our single qubits. For example, here this one, this is the half ice or half by gate, is 99.92, and this means the result is the ice, or the Y gate is 99.89%, and for all the other gate is 99.8. Okay. Now we know the measurement results to 12 qubits, with the 0 is the red dot, the Y is the blue dot, and then let's think about the qubit is at the superposition of 0 and 1, we find the right one. If it's the classical thinking, we will get some thoughts between them. For example, because when I know the qubit is 0, I got down here. When 1, I got the dot there. Then I know half. Then someone may guess it's the middle. And indeed, it looks like this one. And here is the real measurement data from superconducting computer. And so even though we have some noise, but still the fundamental result is the same. Okay, after this kind of single qubit gate, we will do something like vacuum Rabi oscillation between the 1-1 state of these 2 qubits and the 0-2 state. Then from this, we can know the coupling strength between the 2 qubits. Then it will help us to make our 2 qubit gates. After we got our single qubit gate, 2 qubit gate, and we have to look towards the result fidelity for using single solve. Then we got the result on the page, and then the cell qubit. So the final state should be all 0 or all 1 for cell qubit. Indeed, this is what we got. We have some noise, but at least this all 0 and all 1 result is still the dominating result in the end. Okay. Now let's move on to the next chapter. Because we are going to have the hands-on section this afternoon for the quantum computer, so this part I will move through very fast. Okay, first in 2020 we released the world's first desktop programmable quantum computer. It's small, work at room temperature level. Now we have launched a full well-developed desktop quantum computer for research and teaching, which has been sold to the 5 continents. Okay. Let's have a look at the overview. We are going to show you the technique. So have a look at the 3 qubits.
We can only slightly larger than a normal computer and weighted portions of the time. With the software SpinQ, triangle keys for quantum computing education and self-defined quantum algorithm computing very well. The software used for triangle work on the Windows system. It should be installed on a PC or laptop. This is the software of the triangle. It currently supports 2 languages, Chinese and English. system has 6 functions: quantum computing, NMR, user management, task management, calibration, and knowledge. The interface of quantum computing has 4 areas: operation area, result area, information area, sample structure model. There are single-bit computing and three-bit computing in the triangle. In the operation area, we have defined some quantum gates in the system, including single-bit gates and multi-bit gates. You can click the Help button on the right to view the definition of each gate. The 3-bit computing has built-in algorithms, for example, and users can directly choose and run the experiment. To create quantum circuits, we can directly drag quantum gates in quantum circuits. After we build the quantum circuit, if we want to save this circuit, we can click Export to save it as a.txt file. And we can also click Import to import the quantum circuit. Besides, if we want to move all the gates out of the circuit, we can click Clear to delete all gates on the quantum circuit. Before running the experiment, you can name the current experiment as the task name on the left. When we are ready to run the quantum experiment, click Run to start the task, or click Simulate if you only need to simulate. After clicking the Run button, the progress bar at the upper left will display the current experimental progress. Click Progress, and the progress window will pop up, where you can view information such as progress, signals, and parameters. The whole experiment will take about 55 seconds, and the results will be displayed below after the experiment is completed. The light blue bar is the simulation result. The dark blue bar is the experimental result. And the value will be displayed when the mouse is moved to the bar. The lower left shows the molecular structure of the sample trichromato placed inside the instrument, which uses the fluorine analytical loop. This is the quantum computing function in triangle. The nuclear magnetic resonance function. In nuclear magnetic resonance, we can define pulses emitted to perform related physical experiments. We can define the phase, amplitude, and width of the pulse. Then clicking it, the system will display the NMR signal. We provide the pulse according to the quantum gate of quantum computing. Click Import and select.
So, time, we will move on. If you are interested in this, maybe you can show the video again in the afternoon. Okay, and here are some photos of desktop computer user, like some universities, like Hong Kong University of Science and Technology, University Western Australia, and so on, and some middle school, like Shenzhen Middle School is a famous middle school in China. They built a common classroom and started teaching this year. Okay, and if you are interested, we still have common computing competition in Shenzhen every year, and competitors can get some computing training from the teacher before the competition. And now, to this part, let's have a look. What's the half-idle again? We saw the half-idle on the classical computer, and let's have a look what's the half-idle on a quantum computer. It's not something that the quantum computer is good at, but it might help us understand it. The logic gate here represents 0, 1 plus 0, 1 equals 1, 0. and we can use 8 by 8 matrix to represent the state of 3 bits and the operation on it. On them. Usually the state is all 0, and the first operation, the I state, is this matrix, and this matrix, the operation on the middle one. And after this I state, this is what we get, 1, 0, 0. This is the matrix. And then after second pulse, this is what we get. And then after this, the third pulse, after the fourth pulse. And so let's summary the quantum half-adder. Initially, it's all 0. And then beside the initialization, because here we would like to show you 1 plus 1. So I set Q1 and Q2, both of them at 0, 1. And then the result will be shown, then be shown is Q3 and Q2. Then we save a qubit, right? Otherwise, I don't have enough qubits to do the addition. And then after this half-adder logic is complete here. And then this is what we will get the end 1, 0, 1. And then we check the truth table here. We will see all b plus 1 and 1. The result is 1, 0. Okay, that's what we got. You can always check like these different initial like setting like 1 plus 0 equals 0, 1. Okay. But today we took the Gemini, then we have 2 qubits. So this is run on regular. And so we have said something that quantum computer can do, but we know that then what quantum computer is good at? It's good at some complex problems like the vector recognition of large number and or simulation. Like using short algorithm, we can reduce the algorithm complexity dramatically, and this has a big influence on the accuracy system that we are using every day. On the right side, it's on this sense cover lecture paper, 14 simulates the ground energy of biohydrogen atoms. Okay, let's do a comparison between the classical computer and the quantum computer. In classical computer, the heat itself is the voltage here. The voltage is high and low, and the heat is moving around. And in quantum computer, especially like the superconducting quantum computer and NMR system, the qubit itself is the hardware. For example, in superconducting one is on the chip. It cannot be moved around. And for the logic gate, classical computer, the logic gate, the hardware, it's always on the chip or on the PC. And like the logic gate here for quantum computer is a pulse. It's a pulse sequence. For example, you view the pulse of I state, it can go through the qubit on the chip, and then the chip will change from 0 to 1 state. Then mathematically speaking, the basic math logic for classical computer is the addition, while the basic math logic for quantum computer is the metric multiplication. So far, we already have some special tests. Quantum computer is already faster than traditional computer. So in the end, let's do an analogy between the vehicle and the computer. Because of the relationship between car and airplane is so similar to the relationship between classical computer and quantum computer. If you want to go to quantum from Jakarta, you better choose a car instead of an airplane. If you want to do some addition, like 1 plus 1, you better choose a classical computer compared with a quantum computer. We have showed you, most of them we can do 1 plus 1, but since quantum computer is so complex. And then, if you want to go to Beijing from Jakarta, you have to choose an airplane because you just cannot drive there. Then, if you want to simulate some complex chemical material, you have to choose a quantum computer because it's too complex for a classical computer. Right now, the quantum computer is just like the airplane 100 years ago. We can fly, but those that cannot stable and fast. But at least we are in the sky. So that's all what I would like to share today. Thank you.
Well, thank you very much for very nice introductions on the skill of different platforms to do public communications. We have 5 minutes and we can accept a couple of short questions. Please.
I have a question. What is the difference of service cloud and the cloud itself? Is there any more detailed tasks that you can use using the field of quantum computer? And maybe how you can have access to the machine itself? Thank you very much.
We also have cloud includes Gemini on the cloud, and you have access to it through the interface on the cloud. And for the hardware itself, for example, the machine itself, you can do much more than the stuff that you like to do. You can do on the cloud. This is similar like sometimes if you like publish a very nice paper, you just use the cloud from IBM, and usually you cannot get a very good result. You only need to have access to the real machine. You need to spend much longer time. You need to come to the engineer to change something to get a really good result. I think it's because right now is the qubit, not that allowed qubit, so they still have some difference. So the hardware itself is still very valuable and work sometimes. For example, for the you can use it to type the hydrogen dimer and the phosphorus dimer, phosphorus such like. And we searching through, indeed we change many times of our qubits. For example, for Gemini, we use dimensional phosphate, the hydrogen and the phosphate in it to different nuclei. for this triangle, we use this molecular here, and it has 3 fluorines nuclei in it, and luckily they are bonded to each other, and luckily the signal, the NMR signal for fluorine is strong enough. Then I can make the machine small. Otherwise, you need a really big magnet. Then note all the materials can be used as our qubits, especially if you want to like 2 qubits experiment or 3 qubit experiment. If you really want to do 1 qubit experiment, I think every material will be bad. Like you always have some problem in the sample. Like for the water, you can give it pulse. You can change the states of that hydrogen nuclei to from 0 to 1. Always do this measurement. But if you want to have more qubits, it's very difficult in this area. You mean when you try to do something else, like I have more qubits? Now, if some advisor or me, they have done some NMR computer with like 12 or 13 qubits, but for that sample itself is very, very expensive, and the signal is very, very big. So you need to use the best NMR equipment in the world to get the result. Then they have this very good paper, but then that's not what we were focusing on. We would like to make it very cheap, very small, affordable, so we didn't take out this way. But still, people always know the NMR system has many benefits. But the limitation is that we cannot have enough qubits. So this measure we can only use it to do the teaching. But the NMR system is the first system that people have done quantum computing on. The real hardware, like in the 1990s, people already done this kind of quantum computing on NMR system. But recent years, the quantum computing is improving very, very fast. That's not because the NMR, it's because the superconducting quantum computer. Because people finally we can make the qubits by ourselves, unlimited qubits.
Unfortunately, time is running out, so we go to lunch break till 1 o'clock. So please make sure to come back again here. 1 o'clock. I have a couple of announcements to make for those who want to do private prayer. 2 halls around this area. One is just outside the entrance gate. There's a butler halls. And the other one is in the Techno 2 building. Probably it's easier for me to say it in Indonesia. Ada 2 masjid, satu di kedua pintu utama, kemudian satu lagi di Techno 2. Kalau itu bisa jalan kaki, mungkin 10 sampai 15 menit. Kemudian di gedung Techno agak sedikit jauh, maka disediakan 2 mobil, tapi kapasitasnya terbatas, bisa untuk 12 orang ya. Jadi kalau mau ke Techno 2, makan di sana, bisa pakai mobil, nanti ada ribuan yang mobil yang menunggu di depan. Kalau ke Bali umum bisa jalan kaki ke sana.
Barang-barang apa?
Ya. Oke, that's all. Student one. Round of applause for the Thank you.